in the last lecture, or the last two lectures, we talked about the type or the different types of electromagnetic radiation, and we talked about optical telescopes, we talked about interferometry. Today we're going to talk about astronomy from space. It's a small section, then we'll go to the review questions. Now, there are electromagnetic waves, infrared, ultraviolet, X-rays, and gamma rays. I told you that these are blocked by the atmosphere of the Earth. And if we want to look at these radiation that come from space, meaning outside the atmosphere of the Earth, that means we have to do this from outer space. The slide here, it tells you that the X-rays and the gamma rays, they actually interact with the oxygen and nitrogen in the atmosphere. The ultraviolet is blocked by the ozone layer, which is basically O3, oxygen 3. The visible and near infrared, they can basically reach. But of course, the infrared in general, it is blocked by water vapor and carbon dioxide, and that's why we either have to go high in the atmosphere of the Earth, or we do it from outside the atmosphere of the Earth. Of course, radio waves can penetrate in, and this is what we can do here from the surface of the Earth. That's another view again, like windows. We look at the atmosphere of the Earth, and the only two type of waves that can penetrate is basically the visible light and the radio waves. So these the two things that we can do here from the surface of the Earth. And in the last lecture, I told you about the Event Horizon telescope, which was a big project by different groups and so on to get an image of the M87 black hole. Now, when it comes to infrared astronomy, I told you that it either done from higher altitude, or it's best if it's done from outer space. That means outside the atmosphere of the Earth. And you can see here that you have high flying planes. They can be as high as 40,000 feet above the ground. Usually airplanes that you travel in is about 30,000 feet. They go high enough, and they need detectors basically to detect these. And you can see in this photo here, you see a little bit of smoke that basically coming from liquid nitrogen, when liquid nitrogen evaporates and so on. So it is a kind of, this is done by NASA, okay. So it's kind of an operation that needs pilots, co-pilot engineers, and you need scientists on board and so on to detect infrared radiation that comes from space. This is the NASA's Space Infrared Telescope Facility. It's abbreviated as SIRTF, and that basically look at the far infrared radiation, and it has to be done from a satellite in space. When we talk about ultraviolet astronomy, we are looking at wavelengths that are smaller than 290 nanometers. These are completely absorbed by the ozone layer in the atmosphere. Now, if we want to do that, then it has to be done from a satellite, and there are several successful ultraviolet astronomy satellites: IUE, EUVE, FUSE, and these are all basically to detect this ultraviolet. Usually, when we detect ultraviolet radiation, the source that sends this should basically have temperatures in the tens of thousands of degrees, which we call moderately ionized gas in the universe. Now, the Hubble telescope was launched in 1990, and it can basically look at the infrared and ultraviolet and visible as well. So it is basically outside the atmosphere of the Earth, so it avoids the atmosphere that can block the infrared or ultraviolet. So it was extended to include the infrared and the ultraviolet, and you maybe have seen nice photos that's taken from space. Some of them are done by this Hubble telescope. The telescope was launched in April 24, 1990, about 31 years ago. And it orbits at a latitude of about 350 miles or 563 kilometers. And at that time, the telescope basically cost about $2.5 billion. So you can see how expensive this type of research is. The mirror that we have in the Hubble telescope, it's about 2.4 mirror. It's not as big as the one that we have here on the Earth. They actually get to 11 meters and so on. But this is something that you want to put in space. And the Hubble telescope was thought of that it will be ending its mission by early 2000. It's still going, and data is collected from this telescope. Now, this is an image of the Hubble telescope here. Now, there is another telescope that we call the James Webb telescope, and this was supposed to be launched early this year, but I think it's delayed till October 31st, 2021, and we'll see. I think the case with the corona and so on, they delayed things a little bit. This is now more advanced than the Hubble telescope, and that basically can allow us to see greater detail. It's going to be an altitude of about 1 million 1 million miles above the Earth, unlike the Hubble telescope. Let me share my whole screen with you here, just to show you something from NASA website. This is basically the Webb Space Telescope, or James Webb telescope, and the mirror there, it's about 6.5 mirror inside. It's supposed to be launched from the French Guiana island. Okay. It's basically named after the director or ex-director of NASA, James Webb, and they're working on it. Maybe you will hear the news by the end of this year that it has been launched, and then we'll wait for what this telescope can do. So now we even looking at visible light from space as well. So I just want you to be aware that probably something that's going to happen toward the end of this year when we launch the James Webb telescope. Now we have the gamma ray astronomy, that means we want to get gamma rays. Gamma rays are they have very short wavelengths, high frequencies. And if we detect these gamma rays, that means this is coming from violent processes in the universe, meaning very hot temperature. This is known as the Captain Gamma Ray Observatory. There are many nations that collaborated to put this telescope in space. The X-ray astronomy, when we try to detect X-rays, that means when we detect X-rays, that means the area that it's sending this X-rays is highly ionized gas, and the temperature there is about 1,000,000 degrees. And there is NASA Chandra X-ray Observatory, and that's basically what's working on studying X-rays that come from outer space. So there are things that we can do here from the surface of the Earth, and there are things that we can do from space. The last time I told you about the Event Horizon telescope, where groups get together and start basically working here from Earth. I think now they're planning on a bigger project where they're going to even include telescopes from space, X-rays and gamma rays and ultraviolet, and now they're going to combine all of these and how to basically combine the data and get more understanding. So the two, astronomy is an observational science, and they need all of these resources to basically be able to advance our knowledge of astronomy. And in the process, I told you about the spin-offs, things that have been now developed, and it make our life easier. It's because initially it was thought of to help in the observation and astronomy. So that's basically what we need in tools. So if you look about 400 years ago, humans were only relying on their eyesight to make observations. And then with the development of telescopes in October of 1608, and Galileo Galilei made his own telescope, and he pointed that to the sky in 1610. And from that time on, we start basically using telescopes. And now when we talk about telescope, we're talking about different types of telescope, not only visible light. We're talking about telescope that use visible light, telescope that use radio waves, telescope that use gamma rays, X-rays, ultraviolet, infrared. So all of these now, the data that it's collected, okay, it helps us in understanding what we see in our universe, and we try to understand our universe. Now, I must give you a word of caution here, is when you look at some nice images, well, these images are constructed from the different energies of the electromagnetic waves that we receive. And what you see sometimes is artistic rendition of what we actually think it's out there. And we use what I call here on the top false color images. We add this color in, and this has to do with the energy. So when you see a nice image of the Milky Way galaxy, it is not a direct image, but that's how the Milky Way galaxy looks like, because we can look at other nearby galaxies and we can scan through our own galaxy, and we collect the different energies, and then we come with this. So I just try to warn you now that when you look at all these astronomical images, or even when we talked about the Event Horizon Telescope, when they showed the first image of a black hole, they were basically relying on the energy that they received from the waves that they received, and they constructed finally this image. So we have to be careful and not be misled that thinking that this is actually a direct image. By the way, the M87 black hole is about 55 million light years away. So remember, when we actually look at this, we look at things in the past. We don't look at them right now. And that's also an added point when you think that these images are direct images. Are these clear? Any questions on these? So just quickly to summarize what we have done in the whole chapter. Light is electromagnetic waves. The complete electromagnetic spectrum is basically gamma rays, X-rays, ultraviolet, which we call UV, visible light, and I told you that's what we use to see things, infrared, IR, microwaves, and radio waves. Earth's atmosphere transparent only to two electromagnetic windows, visible and radio, and that's basically what we can do here from the surface of the Earth. When we talk about optical telescopes, we have two types, refracting telescopes and reflecting telescope. Refracting telescopes are made of lenses, and reflecting telescopes are made of mirrors. Maybe in the last lecture, if you listen to the recording, or sometimes I wanted to say reflecting and I said refracting. I don't want to. The idea is the most common telescopes now are refracting telescope, because you can make the mirrors bigger. Reflecting telescopes. Refracting telescopes are not. They cannot be made as big to look at things, especially when we need the size of the primary or the objective to be big. So we actually, as I told you in the last lecture, the reflecting telescope basically, when we said the refracting telescope suffer from chromatic aberration, expensive to make, and reflecting telescopes are easier to build and less expensive than refracting telescope of the same diameter. Again, I apologize if you heard in the last recording that sometimes I say that the most common telescopes are refracting telescopes. I meant reflecting telescopes. And in telescopes, we need three powers: light gathering power, resolving power, and magnifying power. And I told you the magnifying power is the one that easily can be changed, but you're stuck with the primary mirror, which basically dictates your resolution. And now, when you want to record the images and so on, we use CCD cameras, and we have other detectors to detect other energies like ultraviolet, X-rays, gamma rays, and so on. And then you have to put all of these together to form a picture. And I think I told you, I think the group that started the Event Horizon Telescope, I think they're planning now to share even telescopes from outer space with different energies, and then they want to come to a final understanding of what they look at. And then we talked about things like active optics. These are techniques they develop over time, and we talked about adaptive optics, okay, where you can basically enhance the images that you look at. And we talked about the technique where we said this is interferometry. And I told you in the last lecture, if we wanted to look at M87, we needed a mirror the size of the whole Earth. But interferometry made that possible. So with this, we end up chapter number 5. Are there any questions on what we discussed? So in this chapter, just trying to give you an idea of how advanced humanity has become in using all of these different range of electromagnetic radiation and the tools. So we want to present it here briefly. We're not going to go in details. I mean, you may actually radio astronomy, it's something big by on its own, or even telescopes and things like that. But we want to give you a flavor of what is used in the in observation in astronomy. Are there any questions on these? Any questions? Good. So what we're going to do next here, we're going to look at the review questions, and this is basically, you know, when I give you quizzes and exams and so on, something similar. But the idea of these review questions is a discussion to what we did. And so the first question here, what is the wavelength of the longest wavelength light, visible light, or light visible to the human eye? You know the range. It's from 400 nanometers to 700 nanometers. So the longest wavelength here is 700 nanometers. I told you about another unit, which we call angstrom, and you may hear that, but it will be 7,000 angstrom in that case. The second question, what is the wavelength of the shortest wavelength visible to the human eye? It is 400 nanometers, or you can also say 4,000 angstroms. That's the visible range for the human eye, but there are other ranges in the electromagnetic spectrum, which basically not visible to the eye. The 3 here, violet light has a wavelength approximately 400 because that's the lowest. Have wavelengths that are longer than visible light. That usually comes into the spectrum. So we start from gamma rays, X-rays, ultraviolet, visible light, then infrared and microwave radio waves. So the only in this and this radiation here, the only one that is longer, it will be infrared. So the answer here is C. There are nanometers in 1 meter. Now, you know that when you're dealing with a meter, you say, I have 100 centimeters in 1 meter. Centimeter is a unit that has been used and it's still used. A centimeter contains 10 millimeters. So we say 1 meter contains 1,000 millimeters. When we talk about micron size, and I told you if you want to relate to it, a human hair, a healthy human hair is about 75 micron. It contains 1 million micron. And when we talk about nano, and you hear a lot these days, nano, 1 meter contains 1 billion nanometers, and you can write that as 1 times 10 to the 9 nanometers. Because you'll be dealing with electromagnetic waves and they're measured in nanometers, sometimes pico and femto as well. Have wavelengths that are shorter than visible light. Gamma rays are shorter, ultraviolet are shorter, infrared and radio are bigger. So actually the answer here is A and B. Astronomers build optical telescopes on tops of mountains because there is less air to dim the light and the seeing is better. So that's why we want to avoid as much as we can from the atmosphere of the Earth. 8, ultraviolet radiation from a star will not penetrate Earth's atmosphere and reach the ground. So if we want to study that, we have to do it from outer space, and maybe outer space here outside the atmosphere of the Earth. 9, a new generation of telescopes is currently being built that overcomes the limitation of the older large telescopes. Some of these new telescopes use segmented mirrors, use mirrors that are very thin and floppy, use active optics to control the shape of the mirror. And that makes it a lot easier to fix mirrors very quickly. Of course, all of the above are used in this. The ability of a telescope to resolve fine detail is known as the telescope's resolving power. And you remember when we talked about alpha min, and I gave you different images ranging from 10 minutes to 1 second, and you can see the difference. But I told you always have to be careful. Resolution has to be in from the start, and then you can magnify. 11. 11. 11. Infrared astronomy is often done from high-flying airplane aircraft because infrared radiation is absorbed in the lower Earth atmosphere. 12. The technique called adaptive optics uses high-speed computer to monitor the atmospheric distortion and adjust the optics of a telescope to partially compensate for the scene. So even in a bad night and so on, you still can carry on with observation. The resolving power of a telescope is a measure of its ability to show fine details and depends on the diameter of the objective. And I told you that also helps in the light gathering power. A telescope that suffers from chromatic aberration right away, it's a lens, so it's refracting, and has low light gathering power, it's most likely a small diameter refracting telescope. Now in this example here, what is the, or this review question, what is the ratio of light gathering power of 5-meter telescope to that of 0.5-meter telescope? Remember when we talked, it basically has to do with the area. So I want to take the ratio of the area of the first one to the second one, and area is equal to pi r squared. So here I say pi r1 squared divided by pi r2 squared. And you know that the radius is half of the diameter. So r1 here can be replaced by d1 over 2, and r2 can be replaced by d over 2. Since I'm taking a ratio, the pi can cancel out, and I can cancel out the 2, even though it's going to be 4, so it can be canceled out. So from here, the ratio will be d1 over d2 squared. So if I use a 5, the mirror is 5 meters, as compared to 0.5 meters, it will be basically 5 over 0.5 will give me 10, and 10 squared will give me 100 times. So just going from 0.5 to 5, that actually enhances my light gathering power by 100 times. What is the magnification of a telescope whose objective has a focal length of 200 centimeters and its eyepiece has a focal length of 0.2 centimeters? We defined magnification as FO, and I told you the O here stands for objective, which is the primary, divided by FE, where E here stands for the eyepiece. So it's 200 centimeters divided by 0.2 centimeters, and that gives you about 1,000 times. And I told you that's probably the power in the telescope that can be easily changed. The others will basically, you have to changing the mirror, and that's something is, or the size of the mirror, and that's something not easy to do. But you can play around with the eyepieces to get more magnification, but more magnification doesn't mean higher resolving power or better resolving power. You do that, okay, from the start, and that has to do with your mirror. The resolving power of a telescope with a diameter of 232 centimeters is, now you know that the formula that we used, alpha min is equal to 1.22 lambda over d, or 11.6 arc second over d. So we put in the numbers and we get here 0.05 arc second. CCD stands for charged coupled device. Observation of radio waves from astronomical objects suffer from poorer resolution than visible observation, because you know that alpha min is equal to 1.22 lambda over d. So it has to do with the wavelength. Visible light have range for 400 to 700 nanometers. Microwave is huge, and that's why they have poor resolution. And that's why I told you when we deal with radio waves, it's best if we use interferometry to produce something with a bigger diameter. Radio telescopes have poor resolving power because radio waves have long wavelengths. Penetrates the Earth's atmosphere and reach Earth's surface. You know that that's only radio waves and visible light. So the answer here, B and C. The Hubble Space Telescope objective mirror is not affected by bad seeing. It's not affected by chromatic aberration because it is a mirror, not a lens. So the answer here, A and B. Probably next year we'll add the James Webb telescope as well here. The Spitzer Space Telescope orbits very far from Earth because the Earth thermally emits infrared radiation at which the telescope is constructed to observe. I told you, you yourself emitting infrared, and there are other sources. So if you construct something to study this wavelength, you really have to be far away from it. So that's why this telescope is far away from the Earth. 24, the main reason for building large optical telescopes on the Earth's surface is to collect as much light as possible from faint objects and improving the resolving power as well. 25, what statement below best describes the refraction of light, the change in direction of a light ray as it passes to a medium of different optical densities. And that's why when you put a pencil inside a glass of water, it looks broken to you. It has to do with refraction of light. 26, the light gathering power of a telescope is directly proportional to the diameter of the primary mirror or lens. And I told you now, when you buy a telescope, they're always rated by the diameter of the telescope. 27, the chromatic aberration occurs in when? Chromatic aberration has to be in refracting telescope when different colors of light do not focus at the same point. And I told you red light has a longer wavelength. It will be further. Blue light will be a little bit not focused at different points, so you actually get a blurred image, and that's the problem with lenses. 28, the main reason for positioning many radio telescopes across a large area and combining the signal is to produce higher resolution images. And I told you about the Event Horizon telescope. Radio telescopes are reflecting telescopes. And probably in your homes now, each one has a dish on top of your home where you're actually receiving signals from satellites. They actually work with radio waves. 30, a telescope whose objective is a lens and contains no mirrors is a refracting telescope. In a reflecting telescope, the objective is a mirror. And the same way we can say in refracting telescope, the objective is a lens. This is a comparison here. Which of the following telescopes has the larger light gathering power? Well, a telescope of 6 centimeters diameter, so you always look for the one that has the larger diameter. 33, the resolving power of a telescope is a measure of the minimum angular separation that can be seen with a telescope. That's what resolving power is. Now, the idea of these review questions is for you to understand why this is the right answer. I can take any one of them, shift it around, or you also have to pay attention to what I say in the lectures, and that's how I'm going to examine you. So the idea here is to give you a flavor of what is used in the observation in astronomy. Now, any questions on these? Any questions? Any question on what we have done so far? Good. So we're done with chapter number 5. Next lecture will deal with